What's up, folks? I haven't updated the video for a while since I'm busy with my thesis defense, and I have passed it now, so I have time to update some new videos. I really appreciate for all you guys to support my channel. Today I will start a new set of videos about varieties of microwave and millimeter wave filters. Filters plays a crucial role in communication system. In this video, I will share the principle of designing a coupled line bandpass filter by illustrating a filter working at 28 GHz. The principle of a coupled line bandpass filter can be found in some textbooks, such as microwave engineering. For a coupled line filter, it looks like in this picture, and it contains many stages. This is stage 1 and stage 2 blah 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 to stage n and stage n+1, and this is connected to the external circuit, and this is also connected to the external circuit. The electric length for one stage is around 90 degrees, and we need to settle down what's the width of this microstrip line and this microstrip line. Another thing we also need to figure out is what's the air gap between these two microstrip lines. This air gap serves for coupling signal from this microstrip line to this microstrip line. And as for this two microstrip line and the air gap, they can be regarded as a planar waveguide. So we can use the planar waveguide to calculate what's the impedance of this microstrip line when it's working at even modes or odd modes. As for how to settle down what the impedance should be, we can use some equations. Such as in this example, we want to design a bandpass filter. Center working frequency is around 28 GHz, and the fractional bandwidth is 10%. The prototype is equal ripple filter. Why we choose to use a equal ripple filter? For a equal ripple filter, it's attenuate much faster in the stop band compared with the maximum flat one. So we use the equal ripple filter. The ripple is 0.5 dB, and we can Google for the equal ripple filter prototype, and we can find some figures looks like this one. Since in our case the bandwidth is 10%, so we find that here, if we want the attenuation to be at least 10 dB, so this coupled line filter should have at least 7 stages. Can check a table called a 0.5 dB equal ripple filter prototype, and we find that when the stage is 7, it indicates what's the parameter, what the 8 parameter should be. And once we find these parameters, we can use these equations to calculate what this value is. In this equation, the delta is the fractional bandwidth for the bandpass filter. In our case, it is 10%. And this G1, G2, and Gn+1 is this value as we settled down. So use these three equations, we can calculate what's this Z0 times J1 is. And once we find these parameters, we put them into these two equations, we can know what's the impedance of this coplanar system when it works at even mode and odd mode. This is the basic idea of how to design the coupled line filter. And we copy this data into a spreadsheet and use these two sets of equations to calculate what the parameter should be. As shown here, we copied what the G is, and this is the Z0 times J, and based on the first set of equations, so we can find all the values here, and then we can use this set of values to calculate what's the impedance of the coplanar waveguide R when it works at even modes. Also, we can find it what the value is when it works at odd modes. And now we have this basic values for the coplanar waveguide. And now we need to settle down what kind of a substrate we are going to use, since different substrates have the different permittivities, and this permittivity and height of the substrates can influence what's the width of the microstrip line and what's the air gap is. In our case, we use the Rogers 3003 substrate with a thickness around 10 mil, which is 0.254 millimeter, and the copper thickness is 17 micrometer, and the 10D for this substrate is 0.001. Permittivity is 3, around 3. Okay, so now we settle down the substrate, and we can use these values to calculate what's the width and what's the air gap for the coplanar microwave waveguide. We can use ADS or tools we can find on website. Since I have ADS, so I just used ADS to calculate what these values are. Okay, let me demonstrate how to settle down this microstrip line width and the air gap with the help of ADS. Now we have opened ADS. We can click here for the tool. We can find that it has a tool called line calculator. Okay, let's start to use the line calculator here. Okay, it appears here. We want to use a Okay, here is this looks like one stage of a coupled line. So we need to settle down what the width is and what the air gap is. In this case, we need to settle down the substrate we used has a permittivity of 3, and the height, the thickness of the substrate is 0.254, and the copper thickness is 0.00017 millimeter, and the conductivity for this guy we just used the copper. It is 5.8, and the roughness, the 10D is 0.001, and the frequency it is not have a big influence, but this one really has a big influence. So the center working frequency is 28 gigahertz, and we want the length, the electric length, to be 80 degrees, right? As we talked before. And we find that for the impedance when it works at even mode, it shall be 69.5. So we just settle down 69.55, and we better change it to millimeter, since when it works at odd mode, it is 39.5 around. So we set down 39.5. And now we can synthesize what's the width is. So we find that the microstrip line for this one, the width is around 0.0498. So we write down the width, and the air gap is around 0.08555. And the length should be in this value, 1.76. So this is around 2 times of that values. So we need to divide this by 2. So we need to write down this length, but here I used it as 2 times of it. So I'd better change it to 189 degrees. And then
For other stages, they are same. We just change what's the odd mode impedance is, what's the even mode impedance is, so we can get these values in the table.
The main thing we care about is the width of the microstrip line and the air gap between two microstrip line, and the length for 180 degrees. But in the design, we just used the 90 degrees, so we divided these values by 2 in our design. Now we have the values here. This is the most important part of a design, since we need to figure out what the value is. The model building part is really simple. So now we have the values, we can start to build the models.
And now we have these values here. We can build a model in CST. So I've already built a model here, but I can show you guys what the procedure is. So I just use the history thing. Okay, I first build up a I first build the first microstrip. I first build the first microstrip lines here, and then goes to the coupled line here, and we goes to the coupled line, and like this we build it by stage by stage by stage. So and now we can run to the final build up things. This is the first stage, this is the second one, and blah 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 continues going. This is a 50 ohm microstrip line used to connect to the system. So I use parameters to settle down what the air gap is and what's the width for each stage. And I got this design, and I simulated them and found some interesting thing. Here is the simulated results. We can find that its center working frequency is a little bit shifted down. It's around 27, not 28. So we need to move this center frequency from 27 to 28. When the working frequency is higher, it means that the quarter of a wavelength is shorter, so we need to settle the microstrip line width to be a little bit shorter. So I optimized it and saved it as other design. I will show you the optimized results.
And I spent a lot of time to optimize this designed filter. And the principle for me, what I did is two principles. First, since we want to move the center working frequency from 27 to 28, so I make the length of the microstrip line for each stage to be a little bit shorter, so its working frequency can go little bit higher. Another thing is I want the magnitude of S21 to be as high as possible. It means that more energy can be thrown from port 1 to port 2 in the passband. So I narrowed this air gap used to couple the microstrip lines. But consider that in reality, we have some limitation for machine this air gap. So based on this consideration, I optimized the results, and the results is showing here, working at around 28 gigahertz. Magnitude is not too low. For the stop band, you can see it's almost lower than 10 dB, so most of the energy cannot pass through. And if we zoom in here, we can find that the magnitude is higher than 3 dB, so it's acceptable for me. It is not flat since this is an equal ripple filter, so I'm not surprised. And we can see it start from around 27.2 and stopped at around 28.7. Currently, it is the best result I can get. Okay, hope this video can help you in your filter design, or at least give you some inspiration for your filter design. If you guys like my video, please give me a thumb or subscribe my channel. And if you want to have this original design file, you can leave your email under the video and I can email you the original design. Okay, thanks for your watching. See you next time.